Welcome to the AIAA Dryden Lecture in Research. My name is Fred Hadier. I'm the Chair of Honors and Award Committee for AIAA. The Dryden Lectureship is one of the most prestigious lectureships bestowed by the Institute. The award emphasizes the importance of basic research in advancing aeronautics and astronautics, and since its inaugural lecture in 1961, it has been a catalyst for sharing research and advancements in knowledge. This premier lecture is named in the honor of Dr. Hugh Dryden, a renowned aerospace leader. He was the director of the National Advisory Committee for Aeronautics, or NACA, as well as the first deputy administrator of NASA when the agency was created in 1958. The 2025 AIAA Dryden Lecture in Research is awarded to an international authority on clean energy and propulsion, Tim Lieuwen. His lecture is titled Future Research Directions in Aero Propulsion and Clean Energy Systems. Please allow me to give you a brief introduction of him. He is a Regents professor and the interim executive vice president for research at Georgia Tech, where he provides overall leadership for its research, economic development, compliance, and commercialization units. He's also founder and CTO, Chief Technology Officer of Technical Logic, an energy industry analytics firm. His work has contributed to enormous commercialized innovations in the energy and aerospace sector. He has authored 4 books and over 500 other publications. Dr. Lieuwen serves on boards of 3 Department of Energy national labs and EPRI. He's the Department of Energy Secretary appointee to the National Petroleum Council, and he's a member of the National Academy of Engineering. In today's lecture, Dr. Lieuwen will discuss how future aero propulsion and energy and clean energy systems will profoundly influenced by broader societal drivers associated with decarbonization, national security, and resilience. He will address these societal drivers and the underlying R&D needs, such as system efficiencies, operational flexibility, emissions, and environmental impact and fuel flexibility. This lecture will span from fundamentals to can applications and unsolved problems and the intersection of combustion, fluid mechanics, and flow stability. If time allows, we will have a question and answer session after the lecture. Please refer to your QR code on the screen and submit your questions. Tim, are you here? Now please join me in welcoming our distinguished lecturers to present the 2025 Dryden Lecture in Research. Dr. Tim Lieuwen.
Thank you.
It's great to see you. Thank you.
All right. Well, thank you. Great to be here. Huge privilege and honor. I've been coming to this meeting, I think, for 29 years, and I've seen a lot of great Dryden lectures, and so it's very humbling to have this opportunity. I thought I would start, though, just by recognizing our 1999 Dryden lecturer, Dr. Robert Lowy, who passed away late last week. Wonderful man. Many of you will have known Dr. Lowy, just super gentle. And if I just think about what I love about my job, what I love about this community, just a combination of world-class expertise and just great people. Maybe we'll just have a moment of silence for Dr. Lowy. Okay, the other thing I wanted to do before I start was just, as with all these things, is so many acknowledgments, so many great longtime collaborators and sponsors. I just wanted to recognize and just my appreciation for the Air Force Office of Scientific Research and the Office of Naval Research, many other federal agencies for their support for our work. Some of the long-term collaborations we've been able to have with with spectral energies, with Penn State, many of people who are here. And then also just wanted to give my deep appreciation for Dr. Ben Emerson and Dr. Vishal Acharya at Georgia Tech and David Wu, who have been such great collaborators at Georgia Tech. So with that, this talk kind of consists of two very distinct parts. One where I've tried to paint a very high level picture, really thinking about societal level drivers. Don't know when, don't know exactly the timeline, but we're clearly on this march towards trying to reduce our environmental impact of humanity. And there's starts and stops and hiccups, but I think the general direction is very clear. So I'll start sort of the first third of the talk, we'll really do that. And then the second third, what I'll do is I'll drill down way much more detail on some of the problems that my own group has worked on over the years that sort of these types of societal level drivers really motivate. So let's start with a kind of a very high level view, and let's assume that we have this goal of zeroing out our climate impacts, of zero CO2, and what's the option space look like? How one might do that, because there's lots of different ways to do this. There's lots of different voices pushing for different directions. There's lots of advocacy communities. There are different people with jobs that live in certain areas which are heavily vested in certain technologies and certain systems. There are existing companies that are heavily vested in existing systems. So lots of different ways to get there. So if we just wanted to kind of say at a very high level, what does that option space look like? You can kind of make this two by two matrix. And the left axis is, well, the bottom one says zero CO2. So let's just say, well, the way that we want to do this is we want to get rid of using the carbon atom, right? We want truly zero CO2. So no hydrocarbons, no fossil fuels. We're talking about hydrogen, we're talking about ammonia, we're talking about electrification, using fuel cells, talking about using solar energy with batteries, things like that. So that is an approach. Another approach is net zero CO2. And the idea there is we emit CO2 in some places, we plant more trees, or we do carbon capture in others. We potentially use biofuels with carbon atoms, where we use the sun's energy to grow a crop and embrace the carbon atom, and then we burn it and we put the carbon atom back in. So those are different approaches. Again, you will see different communities pushing for both of those. The other option space is what I put on the top, is economy-wide decarbonization. So the idea there is, rather than thinking about, well, and really it's probably easiest understood by sector. So with sector by sector decarbonization, the idea is you look at aviation, you look at rail transport, you look at steel making, and you say everybody's got to do their part, everyone has to get rid of their CO2 emissions or their climate impact, and you kind of do it sector by sector. An alternative approach is you say, let's just think about this as an overall system. Let's draw it's probably too complicated to draw a boundary around the whole world, but let's maybe draw a boundary around the United States, for instance, or North America, and just say, what's the easiest, what is the best optimal way to get there, where one sector does maybe more, one sector does less, and so forth. And so this is actually, it's a 2 by 2 matrix, but really you can really divide it into these 3 different regions, because if you're doing zero CO2, it doesn't really matter whether you're doing it economy-wide or sector by sector. It sort of looks the same. Again, lots of voices pushing and pulling and in different directions on what this looks like. If you were to say, as an engineer, let's just say, if you just say, okay, well, what's the least cost way to get there? And by cost, I'll draw maybe a narrower box around that in terms of buying fuel or building transmission lines or building solar panels or making biofuel plants. What's the least cost way? In the top left corner, hands down, least cost way to get there. And it's not surprising, because it's the most general way. It's the one with the least restrictions, or it gives you the most flexibility to do it economy-wide and zero CO2. And working in the top left corner doesn't preclude you from doing everything else. But obviously, if you focus yourself on another quadrant, you're adding restrictions to yourself. And I'll explain a little bit more what this looks like in a minute. So let's start by just thinking about the macro U.S. energy system, and this is an image that I got from Ryan Jones, who works with Evolved Energy Research, who has been very helpful for me as I've been framing up this talk. And you've seen Sankey diagrams like this before, which show the overall U.S. energy system. Over on the left, we have where our energy is coming from. Over on the right is where who's using it, whether it's in heating and lighting buildings or making glass and cement in the industry and in the industrial sector, and then transportation. And then in the middle are all these lines that are connecting this, right? And these lines could be oil pipelines or natural gas pipelines or high voltage electrical transmission lines, but just a lot of plumbing and wiring associated with making this thing work. And if you want to think about the commercial aviation sector, where it fits is in that box right there, other transport. About 2/3 of the other transport is aviation. So just a couple quick comments. Oh, I'm sorry. But if you wanted to kind of sit back and squint and just say, what are the big buckets? What is this thing, if you just reduce some of the spaghetti? Again, we have energy sources on the far left, energy users on the far right. Very, very important to emphasize there's another multi-trillion-dollar sector, which is how we're moving energy around, the energy carriers and energy storage systems that are making this thing work. We have two major energy carriers. One of those is electricity. One of those is fuels, lots of different energy sources. And if you want to just kind of fill in rough numbers of the U.S. energy system today, these are the numbers. And you can see far and away fossil fuels is the biggest source of both where energy is ultimately sourced from, roughly 90%, but also the way in which we move energy around and also the way in which we store energy, right? The Strategic Petroleum Reserve, the natural gas pipeline system, 2 million miles of natural gas pipelines, massive battery, right? And so fossil fuels are actually doing a lot else. The reason the numbers are different on the left and right side for fossils, just thermal conversion efficiencies. But what you can see is that roughly we're running in an 80-20 split with the current U.S. energy economy as a whole, which means that we use fossil fuels roughly as 80% of the means by which we move energy around and store it, and we use electricity as our carrier for the other 20%. All right. So just a couple comments about that. So first of all, it's somewhat obvious, but I just want to emphasize it. These are multi-trillion-dollar sectors, And so as we're thinking about the evolution, it's important to recognize just the interconnectedness of all this. For example, the aviation sector, it's leveraging, it's contributing technologically to, but also benefiting from infrastructure of huge existing industrial sectors, right? Oil pipelines, an oil refining industry, and so forth. The other piece, which I mentioned before, is we think about particularly the fuels, which is the biggest bar, right? The biggest bar in there was fuels, 90% of primary energy sources, 80% of carriers. Fuels aren't just, we're used to thinking of fuels as energy sources, but fuels are actually doing three things to our economy. They're energy sources, but they're also means of moving energy around. They're energy carriers. And they are also means of storing energy. And so a very important point as we think about the future is that those three different value propositions are increasingly going to be separately differentiated, and they're become separately monetized. So what do I mean by that? So today when you buy a gallon of gasoline, you're getting like I said, you're getting three things, right? You're getting something that you can store all that energy around. Your car can sit there for a week, can sit there for a month. You still what it has. It provides the motive power to move your car. And you're not used to thinking about, well, what am I paying for this energy source part versus the energy storage part? But increasingly, those are going to be differentiated. So for example, simple example would be sustainable aviation fuel. The ultimate energy source might be solar energy. So your ultimate energy source could be solar, and then you would use a Fischer-Tropsch process, for instance, to make an e-fuel. So then that liquid fuel would be your energy carrier and energy storage medium. By separately monetized, what I mean is, again, when you buy a gallon of gas, you're sort of, you're buying a gallon of gas, but there's going to be different players along that spectrum who are, and people are going to be making money in different ways. And increasingly, what we'll see is different technologies and systems are going to compete for providing those services, right? So again, like I said, you can have solar and wind as your primary energy source. You can use fossil fuels with carbon capture as your primary energy source. So, in terms of how do we store energy? Well, you can use batteries, you can use compressed air, you can make a liquid fuel, you can make a gaseous fuel, you can make hydrogen, so just a lot of very interesting sort of dynamics in this world as these different value propositions are becoming differentiated in different, as we're watching in real time. And where it's most interesting is in Texas, by the way. The ERCOT grid is we're watching this kind of play out in real time because that's an energy-only market. And it's very fascinating to watch all these different technologies and systems competing within the electric power generation sector specifically. Okay, so let's try to envision, and so don't look at this diagram because I don't want you to be distracted. I should have had a transition slide. What might this world look like in a world where we've zeroed out our carbon emissions? And what might this world look like? So we can tackle this problem as engineers. In fact, there's a large community that exists today, macro energy systems modelers, that try to tackle this question. What they've done is they've done a very sophisticated job of essentially modeling, let's just say we're talking about the United States, modeling the US energy system. And this is like CFD. You can't just sort of average things out, right? You have solar energy here, you have wind energy here, you have pipelines there, you have oil here, you have natural gas there. You have demand centers concentrated in cities. The stuff's all got to get connected. You got to do CFD not only in space, because where this stuff is and how it's getting moved around is spatially heterogeneous, but also you got to do this in time because, in particular, the electric power sector, you got to make this. You've got to make supply and demand match every instant of time. So it doesn't matter if you've got a lot of power at night when you need it during the day. You need either a battery to move it from day to night, or you need a way of generating power during the day. And so anyway, so large communities putting together these models that try to capture all of these features. And once you've got a reasonably high fidelity model of what this energy system looks like, you can then wrap an optimizer around it, right? You can say, hey, this is what we have today. What would it look to get me to some future state? And you can constrain it in different ways. You can say, for example, the way a lot of this optimization works is get me there in a least cost manner. So you have to have a model of cost, and you have to have, obviously there's assumptions with all this stuff. You're modeling cost curves. You're modeling how fast solar and battery costs might drop, what potential, how big the biofuel resource is before you start really crimping food costs and things like that. Anyway, so big community doing this, and what I have here is a picture of what one very prominent group, again, this group at Evolved Energy Research, sort of their prognostication of what a least cost net zero CO2 energy system looks like. All right? And so if you look at the left, you see much bigger solar and wind bars. Again, energy sources on the left, but you still see fossil gas there on the left. You still see domestic crude, so fossil fuels don't go away. And this, again, demonstrates the point that if you just say, I want to get there in a least cost way, as opposed to, I want to get there in a way which is zero CO2 versus net zero CO2, you arrive at a very different answer. On the right, you see your users, and then lots of stuff going on in the middle. You see a big purple hydrogen, which wasn't really there before. You see fuel synthesis, which is synthesized liquid fuels as opposed to using fossil fuel. You see ammonia, etc. So again, if you kind of squint, and then if you say, where is aviation on this? Well, aviation is about 3.1, again, about 2/3 of that other transport sector. Also very interesting is that the fuel split of this least cost model is not 100% SAF. It's 50-50, fossil fuels, renewable fuels. Just going to the point is that if you want to say what's a least cost way for our society to get there, saying aviation should go net zero versus saying how should aviation best support a least cost societal net zero target, you end up at a very different answer. Essentially in particular, you're still burning. And it makes sense if you think about it, because aviation, it's just going to be a whole lot cheaper to manage your CO2 emissions from something that's sitting on the ground, potentially sitting right above a depleted oil reservoir that you can just pump the CO2 right back into than trying to manage something that's flying around and has to deal with all the safety issues of aviation. But just, again, demonstrating my point that you get a very different answer if you think zero CO2 versus net zero CO2, and you get a very different answer if you think sector by sector decarbonization versus society as a whole. All right, so again, so if you sit back and you squint and just say, okay, what are sort of the macro numbers? Here's where they are. You see your energy sources on the left, so big growth in renewables, 55%. But what you also see is, and you see big growth in biofuels, biomass there, but what you also see, again, like I said, fossil doesn't go away. Fossil's still about 20% of primary energy sources, and then the whole idea is then you're utilizing other means to manage and capture or go negative, essentially go negative carbon. On the right side, how is energy moving around? So remember, our current energy system is 80-20. 80% is moved via a fuel, 20% is moved via electricity. You see this least cost world is a 50-50 world. 50% of energy is moving around via electricity, 50% via a fuel. So big growth in electrification, going from 20% to 50%. Lots of opportunities and technology needs and R&D around power electronics and high voltage motors and batteries and energy storage. That's motivated by that. But I want to again emphasize, it's not 100%. And there are groups that are essentially saying that we need a 100% electricity world where fuels aren't utilized at all. And that is a possible world. You can do that. It's just a lot more expensive. And so this least cost world is a world where it's 50-50. What's also interesting about this 50% fuels is it's further split. Half of it is fossil. The other half is synthetic fuels, fuels that you manufacture, hydrogen, sustainable aviation fuels, ammonia, et cetera. And so very large new sector, I won't say completely new, but in terms of getting there for this renewable fuel sector. So that's the United States. So I've shown this to a few international communities and they're like, okay, whatever. This is the world. So this is a model, some of the more recent numbers from the International Energy Agency, IEA, where they've tried to do something similar, where they, again, grid up all the different countries and map these things out. And what you see here is the top set of bars is fuels. The bottom is electricity use. It shows current numbers, 2010. And you see, a lot, again, you see this split between electricity and fuels. But if you flash forward to 2050, again, this least cost world, you see those bars are about the same length. So equal contribution of fuels and electricity. But again, emphasizing that the role of fuels is changing. Significant reduction in the use of fuels as primary energy sources, and in a world now where the primary value proposition of a fuel is a means of carrying and storing energy. All right. So this is my transition slide. So that was kind of my macro societal view. Let's think about what this might mean, and then I want to sort of dive into the weeds on some specific technology problems. Just want to emphasize, there's a lot of really interesting technology questions that pop out of this. And I'm going to emphasize some of the technology drivers in areas that many of you work in and that I work in. But I think, first of all, things like thermal efficiency continue to matter a lot. The Brayton cycle, the rotating detonation engine, whatever it is. If you just think about this world where 50% of the fuels are sourced synthetically, and I can tell you, as much as we're going to try to drive down costs of synthetically produced fuels, it's going to be really hard without a carbon tax to get it at parity to a fossil fuel. I'm just saying. We can have all these wonderful goals to try to get hydrogen or sustainable aviation fuels less expensive than a fossil. It's going to require policy levers, carbon taxes or tax credits or things like that. But what that also means is there's going to continue to be a premium on thermal efficiency, potentially even a larger premium where today, the significant cost of operating an airline is the fuel, significant cost of operating an electric power utility is the fuel. And if we think about these fuel prices, thermal efficiency is super important. Operational flexibility, very, very important. And so what I mean by this is the ability of your system to operate at low power, high power, operate with quick transients and things like that. So this middle image here is the SR-71 doing a high G turn. And you see the flame. You're not supposed to see the flame. The flame has left the building. That's combustor blowout. This would be an example of bumping into an operational boundary on your device, right? And so having systems that are low emissions, high efficiency, but yet don't surge, don't stall, where your flame stays attached, where the system is stable, it's not unstable. You can get all kinds of very interesting but problematic instabilities. Very, very important. And the reason operational flexibility will be even more important is particularly for ground-based applications. If you look at why that 50% fuel shows up, is it just gets a really, really difficult and expensive to have a reliable, resilient system that's 100% electrified. You can do it, it's just more expensive. And so, but what that also means is that these fuel thermal-based technologies are increasingly sort of bearing the load of resilience and reliability for these systems. So operational flexibility, increasing premium. Pollutant emissions, super important. Pollutant emissions are very important today. But I would say, if you think about, I've talked about how there's all these different voices out there pushing and pulling in different directions. And I would say probably the biggest driver towards communities that say, I don't want a net zero CO2 world, I want a zero CO2 world. You might say, well, who would ever want to do that? That's more expensive. It's really, I would say many of those is concerns around what all these refineries and combustors burning fuel means. Because, you know, if you burn hydrogen, you can still make NOx. We know how to minimize it. We're doing a lot of great work. But there's just concerns about NOx and particulates, around just the whole refining upstream sector, how that influences water, land use. But growing premiums on the non-CO2 environmental impacts of these systems, which again is one of the largest, probably the region for the loudest voices that are advocating for a zero CO2 world as opposed to a net zero CO2 world. And then lastly, somewhat obviously, I think is fuel flexibility. Is this is a world, today, if you just think about kind of the fuels that we use, now we're talking about hydrogen at one end of the spectrum, ammonia at the other end of the spectrum, and I mean these things are cats and dogs. And then you've got all these hydrocarbons in the middle in terms of reactivity and flame speeds and just that create all kinds of different issues. And so what I have here on the top right, this is a really cool image. You can see the tip vortex of this airplane. So again, tons of really interesting research problems that flow out of what I talked about in aerodynamics and fluid mechanics and combustion. So there's been a number of talks on contrails at this meeting. And contrails is a super interesting topic because it goes from basic combustion science and just the particulates that are generated by the combustion process, how those evolve as they go through the back end of the combustor, how those interact with the environment, how those are mixed into the ambient, sort of the atmospheric sciences of sort of what the humidity and temperature profile looks like and how that potentially influences our overall CO2, the non-CO2 climate impacts of aviation, which could be quite substantial. Or this bottom right image, this is a little bit more, I've tried to capture 3 different levels of systems, aerospace systems here in these images, and I already talked about the middle one. But the bottom one, this is an image from my colleague Suresh Menon, and you're looking at a cross-section of an aviation combustor, and you're seeing the spray, and you're seeing spray breakup. You see, I don't have a pointer here, I don't think. If I just go over here, you can see over here, this is air coming in, and you're seeing vortices, and you're seeing mixing, and this all plays a really, really important role in soot production, in NOx production, in the life of components afterwards. So anyway, bottom line is, this is a world where there's a lot of really cool problems, and what I want to do in the rest of this talk is really zero in on some of the work which that I've done quite a bit of work on, and just really drill down on some of these more detailed issues, and talk a little bit about kind of fluid mechanics, some of the canonical problems in fluids, how combustion starts to influence those, how you start to get a whole nother set of issues when you start thinking about flame dynamics and then combustor system dynamics. And I put 4 images here of a fern and of a flower and sand dunes and a spider web. And kind of the reason I did that was, nature has this beautiful ways of forming patterns and organizing itself. And one of the points that I want to make is super important practical problems really, really interesting fundamental problems at the same time. That's what makes working in this field so interesting, is we can do really, really interesting basic science work. And really, the way I've structured the rest of this is really to emphasize sort of the way in which nature in our aerospace applications naturally likes to organize itself into really interesting patterns, which all flow all the way up into system level issues around our overall emissions and climate impact. And again, I'll emphasize there's lots of other problems that are really interesting and important. I've just used ones which I'm most familiar with for the rest of this. So let me just quickly talk, just as a quick primer, just to remind ourselves of a couple things around fluid mechanics. And I want to talk about internal flows, like flows inside of a combustor, because that's what I can talk about with the easiest. And so on the left we have a mixing layer, on the right we have a jet, in the middle we have a jet, and the right we have a wake, all very important canonical geometries for internal flows. And what I really want to talk about is vorticity. So the red overlay shows you where the vorticity is. Remember, vorticity is the velocity gradient. And it just shows you where the vorticity is in these flows. And where's this vorticity coming from? If we have a homogeneous uniform flow, you're not really making new vorticity in the flow. Rather, what's happening is vorticity is originating from all those no-slip boundary conditions, all those walls. And you're making vorticity, and then it's getting flushed into the flow. And it's a little bit like if you imagine having a dye, a streak line, for instance, where you're just injecting a dye into the flow, and you say, what happens to that dye as it evolves? Well, if it's just a dye, if it's a flow without any shear, nothing really interesting. It just convects downstream and it gradually diffuses. So the next question is, well, essentially that far left image is a little bit like a dye. You're injecting vorticity into the flow, and what happens to that vorticity? Does it just sort of go downstream, and does it diffuse, or do more interesting things happen? Well, to answer that question, I want to talk a little bit about how vorticity interacts with itself and so if we start with a single vortex, here's what I have here. So this black dot denotes a single vortex, and it just spins. That's what a single vortex does. But the moment you start getting multiple vortices, interesting things start to happen. So if I have two counter-rotating vortices, the right vortex is inducing a motion on the left one. It's pushing it down. The left vortex is inducing a motion on the right. It's pushing it down. So these two vortices are actually going to translate. They're going to convect. So if you've ever taken a canoe paddle and been in the water, and you move the canoe paddle through the water, you will see this. You'll see those two vortices formed at the edges. If you lift your canoe paddle out of the water, you'll see those two vortices continue to translate and convect through this exact phenomenon. Well, all right, let's make this a little bit more interesting. Suppose I take a linear array of co-rotating vortices. So I've got a whole bunch so what I've done is each white dot here denotes an individual vortex, and I've just drawn a black line through them just so you can show how they're connected. And this problem is actually motivated, it's not the same thing, but it's motivated by this sort of shear layer profile here, where you have that jump in vorticity in the middle. And so again, each one of these vortices is inducing a motion on each one of the other ones, and so if you just leave it like this, it'll stay like this, and it'll just diffuse downstream and nothing interesting happens. But it turns out that this configuration is unstable. So what happens if I just take these vortices and I perturb them a little bit? What happens to these things? How does it influence how they interact with each other? Turns out that this was a problem that was looked at by Rosenhead in 1931, and I'm just reproducing their results, which shows you how it happens. Again, each one of those white dots is the vortices, and as you watch this thing evolve, what you'll see is these things start to move. They start to move relative to each other. They start to concentrate. They start to roll over on top of each other. And so if you just aggregate or add up the total vorticity in the flow, it hasn't changed. It's just organized itself. It's concentrated itself. And this looks a whole lot like this nice picture from Ho and Ware from Annual Review of Fluid Mechanics. And we call this basically this fact that shear layers naturally, they don't want the vorticity to remain diffuse and spread out. They like to concentrate that vorticity. We call that the Kelvin-Helmholtz instability, which is ubiquitous in nature. Ubiquitous in nature. And here's just a couple images. Cloud pattern in the sky, sort of the classic Brown and Roshko image, just showing the way that vortices naturally want to organize themselves and concentrate themselves. And this has order one influences on essentially every problem that those of us in this room are interested in. It's because this organization of vorticity into these large-scale structures that plays such an important role in how things mix and acceleration of mixing in so many important combustion and gas turbine and aerospace and aircraft engine and overall aerospace vehicle problems. All right, well, let's make this a little bit more complicated. Let's do two linear arrays of vortices now. So I've got white dots is a whole bunch of vortices rotating in one direction. The black dots are vortices rotating in another direction. Again, the line is just drawn there so you can see where they are. This is not the same thing, but again, it's motivated by the problem of a wake, right? In a wake, you have these two vortex concentrations of the flow separating off of the two. And what happens if you perturb this problem? What if you perturb those? Well, this was a problem that was looked at in 1962 in this JFM paper that I have here. And this just shows what happens as you march this thing down in time. And again, what you see is this configuration is unstable. And if you go to the bottom image, what you'll see is all those dark vortices have clustered together and all the light vortices have clustered together. They're staggered. And you see something that looks a whole lot like what we call the von Karman vortex street, which is something you will all be familiar with, which again, ubiquitous in nature. You know, this top left image, it's an image from a satellite showing clouds over a volcano in Hawaii. Top right image, this just shows an oil tanker grounded on a rock, and you're looking at the oil slick. The flow is moving, and you see these other images. But what's happening here is that you have some source of, you have this vorticity wanting to coordinate and to concentrate. And then what you can start doing is start looking at more and more complicated flows that look more and more like things that we make thrust vectoring devices with, or that we mix fuel and air with, or that we mix air, we cool off airstreams with. So for example, a jet and crossflow, much more three-dimensional, but again, what happens is this vortices don't just go everywhere. They like to concentrate. They like to form patterns. In this case, you get some very classic organized vortical structures. Or you can have two jets and crossflow. This is starting to look maybe like an RQL combustor, an aviation combustor. This is some work done by Arvind Chand, who's at this meeting. And the vorticity starts to talk to each other. You can get even more 3D if you start looking at things like swirling flows, where the flow starts spinning. Many aircraft engine combustors, you have annular flows where the flow is spinning. You've got multiple shear layers in both the streamwise direction, the azimuthal direction. This is an image from Dr. O'Connor at Penn State. These are some computations of this kind of flow from Vigor Yang at Georgia Tech. And again, what do you see? You see this vorticity, which comes from no slip conditions at the walls of your inflow, organizing itself, in this case, into these very nice spiral helical patterns. All right, so that's kind of a baseline. Now, if we start thinking about what happens if we start adding variable density, if we've hot and cold streams, or if we add combustion, well, this is the only equation I'm going to show you. Combustion, there's different ways in which combustion influences what I just showed you. It can accelerate the flow. It can stretch vortex lines, making them more intense. It can bend them. It causes, the flow dilatation is a really important one. Just like an ice skater, if they move their arms in or out, they spin faster or slower. Combustion does that. It makes vortices get spread out, or you can get mechanisms for generation of vorticity like the baroclinic torque. But I think the main point I want to make here is if we go back to this image that I drew before of these two arrays of vortices, and essentially what's going on is each vortex is talking to every other vortex, right? They're inducing motion on them. Well, one of the really interesting things combustion does is, imagine I have a magic membrane, which I just drew with this red line, is it influences how these things are talking to each other, right? Through gas dilatation, not only is combustion a super important practical thing that we all have to deal with, but it also is a super interesting fundamental thing, because what it is it's a knob that you dial that, depending on the gas expansion ratio, that changes how these different vortices interact with each other. So for example, this is an image from Mario Sotirio and Rob Erickson, which shows you what happens if we have a wake flow. So top image is your classic von Karman vortex street. So the color denotes vorticity. So you see this organization of vorticity into these blobs. It organizes itself. And then what we do is we start moving down as TB on TU denotes the gas expansion or the temperature ratio across the flame. So the black line denotes an instantaneous flame image. And as you start marching down, what you can see happening is you lose that von Karman vortex street. Really, because in this case, what the flame does is it really starts to block how those two shear layers are talking to each other, interacting with each other. They're still unstable. They're just unstable in different ways. Or this is another image. This is from my colleague Ben Emerson at Georgia Tech. You're looking at again, a video. This is experimental data of a flame. The top right is a spectra. It's a Fourier transform of how much the flame is flapping around. And as we move to lower temperature ratios, so a temperature ratio of 1 essentially being isodensity, notice how that peak pops up in the spectrum. This is not an acoustic tone. This is just the natural von Karman vortex street, Struhal number 0.2 type tone that happens because these shear layers are interacting with each other. So this gas expansion ratio is super important from a practical point of view, because if you can imagine, if you're running an atmospheric pressure flame like your home water heater or a boiler, you've got air at 300 K, when you burn it, it's going to pop up to maybe 1800 K, gas expansion ratio or temperature ratio of 6. Big change in how you're influencing vorticity. If you think about like an afterburner, an augmenter, a thrust augmenter, air is already coming in really hot. You might only bump up the temperature by 1.7, maybe 2, starting to look much more isodensity. If you look at like the main combustor in a gas turbine, it's come through the compressor, it's hot. You might have a temperature rise of 2.5. And so you get very, very different, very fundamentally different regimes of how these fluid mechanic instabilities are manifesting themselves in these different types of environments based on this gas expansion ratio. Then, again, this is an image of a combusting jet in crossflow. So here we have a fuel jet and air. They are burning. So what the orange denotes is an instantaneous shot of the OH radical, and you can see the flame and the flow talking to each other and interacting with each other through these interactions. And one of the things that's really interesting about this is that where the flame sits is really important. So in these images, there's two different configurations. One is I have fuel coming into air, and the other is air coming into fuel. The blue denotes where the shear layer is, where the vorticity is concentrated. The yellow denotes where the flame is sitting, where all this gas expansion is happening. So, and then the bottom images show a cut. And so what you'll see is the bottom right image, notice where the shear is, it's a circle. You get this ring vortex, and one part of the ring is the vorticity is interacting with the other side, and that's why ring vortices are unstable and things like that. You stick a flame in the middle, you start blocking that interaction of vorticity with each other, versus on the left, the flame's sitting on the outside. It really changes that interaction. And so, so the top left might represent a configuration like in a modern, if you look at what's called axially staging in modern, really high efficiency gas turbine power plants on the ground for ground power, you might have this configuration, whereas the top right might look something more like the quench section of an RQL combustor, where you're basically dumping air into a fuel-rich crossflow. Okay, so that's just a couple examples of just the way the flow naturally organizes itself, how combustion changes that organization. What I want, and I'm going to start moving faster because I'm going to wrap this up in a minute, but what I also want to emphasize is that in addition to the flow, the flame has its own dynamics. The flame is doing its own thing. And so what I have here is an image of a bluff body stabilized flame. And so if you have a flow and you have a flame, you'll get a flame that spreads off of that. And what we've done is we've just shaken that bluff body from side to side. And what you can see is you're creating these wrinkles on the flame. These wrinkles are convecting downstream. They're evolving as they convect downstream. And so the flame is doing its own thing. And so that's interacting with the flow. And so one really interesting thing here is that, for example, if you look at a turbulent flame, so flow's going bottom to top, and you just draw a whole bunch of instantaneous images of where the flame is, this is a pretty typical picture. And you see what we call the turbulent flame brush. Where the flame sits occupies a wider and wider region as you go downstream. Sort of like a turbulent diffusion process. The flame's getting knocked around more and more as you move downstream. At the bottom, it's not moving around much just because it's attached, it's anchored. Well, in many of the problems that we think about, where we have these natural instabilities or this natural self-organization, we have harmonic forcing on top. And so this is an image, same geometry, where we have harmonic forcing. And what we can do is, so if we look at the right, where I've overlaid all those instantaneous flame images, you see a different picture. You see the amount of flapping the flame is taking, it's getting more, and then it actually gets less. Well, that's kind of weird, because if you think about, if you're modeling this growth and where the flame sits as a diffusion process, that would imply maybe negative diffusion or something. So that's clearly not what's going on. And so we can be a little bit more quantitative. So if we just grab the instantaneous flame position, we call that L, which I've shown here with the red, L is a function of downstream distance x, it's a function of time. And what you can do is actually, if you cook up, you can put together a simple model. Actually, this is the only other equation I'll show in this talk. You can come up with a simple model of how sort of these periodic convecting disturbances interact with the flame. And what happens is that when you perturb a flame, whether with an acoustic wave or a convecting vortex, that interaction actually creates new length scale disturbances. It creates interference patterns. And that interference pattern is controlled by how fast vortices move versus how fast waves on flames move. So like I said, flames have their own dynamics. They support waves. You have waves that propagate on flames. And if a vortex is not moving at the same speed, what's happening is you have two periodic disturbances. They're moving at different velocities. Some points are in phase, some points are out of phase. And you get this interference wavelength. And we see these things all the time in flames. This is data taken by Santosh Shanbhogue at MIT of magnitude of flame flapping as a function of downstream distance. And you see locations where it's flapping a lot and where it's not flapping much at all. Last example that I want to give before I wrap up is I've talked about the flow, adding combustion, add the flame, now add the overall system, is combustor systems have their own dynamics, right? Here's a really nice image from Nicholas Noiret at ETH showing some of these combustor system dynamics. The right image is some work that we did, and you're looking at a visualization of the natural acoustic modes of a combustion system. And what happens is combustors are like organ pipes. You know, they have natural acoustic modes. You can get lots of frequencies, not one, but many, many frequencies. They can couple. This is an image from Chris Douglas at Duke University. So in many cases, what happens is flames make sound. Sound excites hydrodynamic instabilities. It excites a flame. So you get all kinds of really beautiful and fascinating, but very destructive instabilities in rockets, in home heaters, and aircraft engines and we call these combustion instabilities. And again, often these acoustic instabilities are driven by vortex flame acoustic coupling. And so this image on the right is a movie, again by Santosh Shanbhogue at MIT, of a flame where you're forcing and you can clearly see the excitation of those vortices. So I will stop there and just to summarize, lots of interesting problems. A net zero economy is not what you think it is. It's not a world of 100, lots of electrification, but not 100% electrification. Lots of fuels, lots of renewable fuels, but still fossil fuels and things like that. I want to give a big appreciation to Trevor Kicklighter and Guru Ganesh, two of my students who helped me identify, pull together a lot of these great movies. And I have to conclude with a little self-advertisement from my textbook, Unsteady Combustor Physics. So thank you all.
It's my pleasure on behalf of AIA to present to you this medal and appreciation plaque that is here. And we'll be having the pictures first taken, and then we answer the questions.
Sounds great. Thank you.
So Tim, thank you so very much for extremely informative presentation. We really enjoyed it. So this is your
thank you.
Medal. And so this is an appreciation to an outstanding presentation that you just made and contributions in the field.
Great.
So again, on behalf of AIA, I really appreciate that. Now the pictures, oh, there we go.
We're here. All right.
So this not it? Okay.
Thank you.
Thank you so much.
Yep.
All right, we do have, why don't we just sit down right here?
All right.
We do have, I was without any exaggeration, a large number of questions. And we do have 5 to 10 minutes to do that. Maybe I answer the most difficult question first. And would you be willing to meet with your students after this lecture?
Absolutely.
Okay, so
yes.
Whoever posed that question, you got your answer, so please see him after this presentation. So I go through, again, large number of these questions. I picked a few. How do you think the increase in rocket launches would affect the decarbonization issue?
Yeah, no, that's a great question. It's one of these, it's like a little bit like data centers and large language models, which is just this massive disruption in business as usual. And just think, I mean, what's it going to mean? It's going to mean global telecom. It's going to mean I don't know, maybe the end of cell towers. I don't know.
Yes.
I'll have great cell service when I'm out hiking in the wilderness.
Yes.
And I think I would suspect, though, that the overall carbon footprint of that is going to, those direct launches will pale relative to other sectors.
Right.
But the macro influences on society, there's going to be major follow-on secondary influences just due to what those, just having massive satellites and satellite communications will enable just societally, which I wouldn't even want to try to speculate on.
Right. I think that the same person is asking another question that says that you did not mention the nuclear energy and how is that there? With the
so nuclear shows up in all those slides that I showed the current sector and the future sector. So nuclear is really, really important. And one of the, I think it was 15% of the of a net zero economy. If you think about kind of the picture that I showed you, and you say, what would make what does a least cost net zero world look like? And you say, well, what assumption would you, if you tweaked an assumption, if you did a sensitivity analysis, what assumptions could have the biggest influence on fundamentally changing your picture of what a least cost net zero world looks like? And that would be low cost nuclear. If in fact we could solve this problem of low cost nuclear, it would totally transform what that least cost net zero world looks like.
So each sector and each application area for green energy calls for a different type of energy. So there's no really one that would be responsive to every areas of application. So what do you think, for example, you can see wind energy, solar energy, they don't really, their main emphasis is not so much decarbonization, but the other factors that comes in terms of funding, availability, when there's wind, people use wind. Mm-hmm. So where do you think the most dominating and impacting of all the variables that is here comes in for the selection of a green energy?
So, I think what's playing out today as we speak is, the largest source of new nameplate capacity is solar energy, because solar energy, the costs have just plummeted. And we will watch this play out. So Trump in the White House, Biden in the White House, doesn't matter. Solar energy is really, really inexpensive, and we're going to continue to see a lot of build out of solar energy just because it makes sense on a cost point of view. But what we will also see happen, and again, you can start seeing this in certain markets, particularly Texas and California, where you have a lot of non-dispatchables, wind and solar, is that they are, and there are some days in Texas now, and the reason I'm highlighting Texas is its own grid. It's islanded from the rest of the country. There are days where 50% of the power comes from wind.
Yes.
And so you're basically having to build a system that can manage that. And so when solar and wind are 3%, 5%, you just stick them in there and the rest of the system accommodates. When they start to become 50, 60%, 75%, then a lot of other considerations become really important. And basically having firm dispatchable power, like nuclear,
right,
like natural gas combined cycle power plants, become really important.
It's an interesting question here that connects the emerging autonomy emphasis and autonomous systems to the choice of the fuel. Now, how do you think that relationship crosses when it comes into the carbon and use some of the energy sources that you said? Yeah,
so a fascinating question as a society is what do our energy carriers look like going forward? And I showed you, probably there's a lot of agreement that roughly 50-50 of our energy carriers come in the form of an electron versus 50% in the form of a molecule. But then the next question comes, what should that molecule look like? Should it be something that looks like what we use today that can drop into existing infrastructure? So in other words, do we essentially make molecules that look a lot like fossil-derived fuels but are generated completely renewably? Or do we say, let's move to something, if we could design the system from scratch and have a molecule that would be maybe cheaper to produce, be safer, and so lots of interest today in hydrogen and ammonia and methanol, in other sort of non-drop-in things that you can't just drop those into an existing aircraft engine or an existing power plant or an existing home furnace, right? And so then you start having to transform infrastructure. So frankly, what I think is going to happen is the existing infrastructure is just too vested, too deep, and I see a world where we're going to be doubling down on drop-in renewable fuels that look a lot like current fuels, whether they're liquid, whether it's a natural gas or a liquid fuel.
Very exciting. This question is not so much focused on the theme that you've been presenting, but the question here is that what do you think is the most exciting area of research in aeronautics?
Oh man, game on! You know, there's like so many. You know? I mean, electrification of aviation, so interesting. Hybridization of sort of the hybridization of thermal systems with electric systems. You know, the ability to completely rethink architectures, super interesting. Thermal energy, you know, just what's happening in terms of gas turbines and thermal energy devices, what's happening in rotating detonation engines, if we can actually figure out. So there's just, I mean, I wouldn't even want to speculate on a single thing. I'd like to live 4 parallel lives.
Yeah. And then I think that this question that just came in, it kind of tests what your intentions are here. It says that if you had $1 billion cash in R&D money, which areas of research and energy would you put it in?
So, I mean, I would, if I just look at those pictures that I showed you, we're moving from a world of 20%, where electricity is a 20% carrier to 50% carrier. Electrification is, there's just so many interesting opportunities which make money today. The fuels, I work in fuels, fascinating topic. It's so driven by regulatory and policy levers. These electrification technologies make sense today. So whether it's aviation, power, communications, there's just lots of really interesting things happening.
Right. I would say this would be probably the last question, and it says that what do you think the impact of the upcoming administration is going to have on the zero CO2?
So, yeah, it's a great question. I'm spending a lot of time thinking about this question, and I think, so just a couple observations is, what's the biggest hang-up today towards deployment of renewable energy? Yeah. It's siting. So if as a nation we can, if Elon Musk and Vivek Ramaswamy can tackle the siting, the regulatory issue and make it possible so that we can build infrastructure, that would be transformative for renewable energy. Yes. We've got so many wind assets in the Midwest that we can't build because we can't get the power out. Yes. So that's an example on the plus side. I think on the other side is, simply put, we as humans are impacting our planet. And we've got to get our arms around this thing. And I think the worrisome part is not acknowledging and reference in taking serious. Because at the end of the day, I think we need to acknowledge the influence of carbon on our atmosphere, and we need to price that. We need to monetize it. And I don't see any energy towards doing that.
Okay, well, thank you so very much. This was truly informative, very enlightening, and extremely well-deserved.
Thank you.
For you. Thank you so much.